All right, we are at section 29.2, the magnetic force between two parallel conductors. Before we get into uh, before we get into the PowerPoint, let me just do a little demonstration here. This is a Wolfram Mathematica demonstration. When you have wires, parallel conductors, and they're both carrying a current, this is an important feature that's to remember. If you look at you have a conductor here, carrying I1, and you have a conductor next to it, I2. Notice the force lines, the blue force lines, they are directed towards each other. So when the currents, parallel currents that are running in the same direction, the force on the wires is towards one another. And you can see as we decrease the radius separating the two, the force gets bigger. As we decrease the radius, the force gets smaller. Now, let's just pick some nominal value. In fact, I think I can enter in a value of, we'll just say 3, and let's and make this value 5, so that it's the same as the one below it. There's 5 amps of current going through each one, and so it's generating a force of on this side minus 1.667 times 10 to the minus 4 newtons per meter. Now let's see what happens if we reverse the current. Let's make this a minus 5. Oh, look what happened to the forces. Now they're going outward. So if you have currents going in opposite directions, two parallel conductors with the currents going in opposite directions, the force opposes them. They'll be away from each other. Back to positive 5, and you'll see that the force is directed towards, and then make it negative 5, it's outward. So with that little demonstration, let's go to the PowerPoint. Okay, so we see the field B2 due to the current in wire 2 exerts a magnetic force of magnitude F1 equals IL B2 on wire 1, I1 being the current in conductor 1. So force equals I1L times B2. Well, what is, and F1, so since L cross B, the 90 degrees, so it's LB sine theta, sine of 90 is equal to 1. So it's I1 LB2. Force is equal to I1 LB2. What is B2? It's mu 0 I2 divided by 2 pi times this A being the separation between them. 2 pi A, where A is the separation between them. So let's just bring the I into the parentheses, and you have the force on 1 is equal to mu 0 I1 I2 divided by 2 pi A being the separation distance, times L. So the force on B, the magnetic force divided by the length is equal to mu 0 I1 I2 divided by 2 pi A, where A is the separation distance. I apologize about the dogs barking. I can't do anything about it. So this is actually used to define the force between two parallel wires is used to define the ampere. When the magnitude of the force per unit length between two long parallel wires that carry identical currents are separated by 1 meter, when the force is 2 times 10 to the minus 7 newton per meters, the current in each wire is defined to be 1 amp. So the force of the magnetic force per unit length per L is equal to mu 0 I1 I2 divided by 2 pi a. Force 1 is equal to mu 0 I1 I2 divided by 2 pi a, where a is the separation distance and L is the length. Okay. Now, a loose spiral spring carrying no current is hung from a ceiling. When a switch is thrown so that a current exists in the spring, do the coils move closer together, move further apart, or they don't move at all? Well, let's think about it. You've got this coil, so the current is going in the coil. So from what I showed you on the little Mathematica demonstration, whenever they're traveling in the same direction, they are drawn to each other. So at each coil, the current is going to be going in the same direction. So they're parallel conductors, but they're in the same direction, so they should move closer together. And yes, there's the answer. They move closer together. Okay, and we'll stop there. Next section, 29.3 is Ampere's law.